This lecture is one in a series of 3 lectures on the error formulas of certain numerical integration techniques that belong to a class of techniques called Newton-Cotes techniques. This series of lectures covers the error formulas for the midpoint rule, the trapezoidal rule, and Simpson's 1/3 rule, or plainly Simpson's rule. This lecture covers the error formula for the midpoint rule. The midpoint rule is frequently used to estimate the integral of a function f over an interval from x equals a to x equals b. If the function f is greater than or equal to 0 and continuous, then the integral of f from a to b can be thought of as being the area underneath the graph of f and above the interval from a to b. We subdivide the interval from a to b into n subintervals. We will simplify the discussion in this lecture by choosing what is called a uniform partition. That is, the n subintervals will all have the same length. Let h be equal to the length of each subinterval. Then h is equal to b minus a divided by n. We determine the partition points or the nodes of the interval. We can start by designating a to be equal to x sub 0, followed by x sub 1, x sub 2, all the way through x sub n, with b being equal to x sub n. The graph uses 4 subintervals, and therefore n is equal to 4, with b being equal to x sub 4. Then we determine the midpoint of each subinterval. We designate these midpoints as m sub 1, m sub 2, all the way through m sub n. If it is indeed the area underneath the graph of f that we are estimating, then we estimate the area over each subinterval using a rectangle whose height is equal to the y value at the midpoint. To derive an error formula or an error bound for the midpoint rule, we will work with just the first subinterval and then generalize to dealing with n subintervals. To proceed with finding the error bound or the error formula for the midpoint rule, we take a look at the Taylor series of f around the midpoint m sub 1. F of x is equal to f of m sub 1 plus f prime of m sub 1 times the quantity x minus m sub 1. If we take only these two terms for the Taylor approximation, to maintain an equation, the next term would be the error term, which is given by the second derivative of f evaluated at some value c which depends on x, and this is divided by 2 or 2 factorial, and then this fraction is multiplied to the square of x minus m sub 1. Here, c of x is a value that lies on the interval that contains x, x sub 0, and x sub 1. We define a new function capital F so that capital F prime is equal to f of x. That is, capital F is an antiderivative of little f. We invoke the fundamental theorem of calculus, or at least one version of it, so that the integral of f of x with respect to x from x equals m sub 1 to x equals t is equal to capital F of t minus capital F of m sub 1. To determine the value of this expression, we find the antiderivative of little f using this expression. Little f applied to m sub 1 is a constant, and so we can write down f of m sub 1 times x as an antiderivative of this constant term. But instead of doing that, we will use f of m sub 1 times the quantity x minus m sub 1. Do check that differentiating this expression with respect to x gives us back f of m sub 1. Integrating this term with respect to x, we get f prime of m sub 1 times the square of x minus m sub 1 all over 2. Now these two terms make up the antiderivative of the first two terms in the Taylor series of f. We still have to evaluate these two terms at m sub 1 and at t. To complete the equation, we still have to integrate the error term with respect to x from x equals m sub 1 to t. We are now going to use this equation to obtain an exact formulation of the integral of f of x from x sub 0 to x sub 1. We hope that this exact formulation of the integral of f of x from x sub 0 to x sub 1 is one that we can compare to the midpoint formula rule for estimating the integral of f over the first subinterval. By doing so, we hope to get a formula for the error. Using the fact that capital F is an antiderivative of little f, the integral of little f from x sub 0 to x sub 1 should be equal to capital F evaluated at x sub 1 minus capital F evaluated at x sub 0. To determine capital F of x sub 1, we plug in x sub 1 for t in this equation. Plugging in x sub 1 for x here, we get f of m sub 1 times the quantity x sub 1 minus m sub 1, plus f prime of m sub 1 times the square of x sub 1 minus m sub 1 all over 2. There's nothing we can do about this integral except to write it down. Observe that by plugging in m sub 1 for x, everything cancels out in the boxed quantity, and so we get 0 when we plug in m sub 1 for x. We should end up with a very similar formula for capital F of x sub 0 minus capital F of m sub 1. This turns out to be little f of m sub 1 times the quantity x sub 0 minus m sub 1 plus f prime of m sub 1 times the square of x sub 0 minus m sub 1 all over 2. And then we have the integral. This time the limits of integration are from m1 to x sub 0. Now remember that m sub 1 is the midpoint of the interval from x sub 0 to x sub 1, which is h in length. Therefore, x sub 1 minus m sub 1 is equal to h over 2. And x sub 0 minus m sub 1 is equal to minus h over 2. If we take this equation and subtract this second equation, note that we do get capital F of x sub 1 minus capital F of x sub 0 on the left side. After all, that is the quantity that we are after. With capital F of m sub 1 cancelling out, we are left with capital F of x sub 1 minus capital F of x sub 0 on the left side. On the right side, we have little f of m sub 1 times h over 2 minus little f of m sub 1 times negative h over 2. Now h over 2 minus h over 2 becomes h over 2 plus h over 2, which is equal to h. And so the first term is equal to little f of m sub 1 times h. The square of h over 2 is the same as the square of minus h over 2. And so the first derivative terms from the two equations cancel out. The only thing left will be the difference between the two integrals. Observe that in the two integrals, the integrands are the same. The lower limits of integration are also the same. And so we apply a property of integrals so that we can write the difference between the two integrals into a single integral. The upper limit of this integral will be the upper limit of the integral from which we are subtracting. The lower limit will be the upper limit of the integral that we are subtracting. Finally, we write down the integrand to complete the formulation for the integral of little f over the first subinterval. Let us examine the first term on the second line. The first factor, little f of m sub 1, represents the height of the rectangle on the left panel. Little h represents the width. And so this product represents the area of the rectangle on the left panel. This is the midpoint approximation for the integral of f over the first subinterval. This integral term, which is extra, must be the error term. We call it error sub 1 since it is over the first subinterval. We take the absolute value of both sides of the equation to determine how bad error sub 1 can get. We bring the absolute value inside the integral so that we end up taking the absolute value of each factor inside the integral. This produces an integral that is at least as big. Now, very often, the value of c of x will be very difficult to find, if not impossible to find. And so to cover as many cases as possible, instead of using c of x precisely, we use the maximum value of f double prime on the subinterval. Of course, since we are using the maximum absolute value of f double prime on the subinterval, we get a quantity that is at least as big. This fraction is a constant, and so we can bring it out of the integral. And so we end up with just the integral of the square of x minus m sub 1 over the first subinterval. Observe that we have dropped the absolute value sign for this squared quantity, since the squared quantity is non-negative. Integrating the square of x minus m sub 1, we get the cube of x minus m sub 1 all over 3. And this we evaluate from x sub 0 to x sub 1. Using the fact that m sub 1 is halfway between x sub 0 and x sub 1, so that x sub 1 is equal to m sub 1 plus h over 2. And x sub 0 is equal to m sub 1 minus h over 2. This last expression ends up being equal to the maximum of the absolute value of f double prime sub 1 times the cube of h all over 24. The absolute value of the total error then, when using the midpoint rule when estimating the integral of f over the entire interval from a to b, should be less than or equal to the sum of the absolute values of the different errors. We define capital K to be equal to the maximum of all the maxes of the absolute value of f double prime over all the different subintervals. Capital K, it should be noted, is equal to the maximum of the absolute value of f double prime over the entire interval from a to b, assuming of course that f double prime is continuous over the entire interval. Each of the n terms on the right side of the inequality is less than or equal to capital K times h cubed over 24. And so the absolute value of the total error is less than k times h cubed over 24 times n. Multiplying the right side of the inequality by n squared over n squared, and taking advantage of the fact that h is equal to b minus a all over n, or h times n is equal to b minus a. H cubed times n cubed is equal to the cube of b minus a. And so the absolute value of the total error, that is the absolute value of the integral of f over the interval from a to b, minus capital M sub n, where capital M sub n is equal to the midpoint rule estimate using n uniform subintervals, is less than or equal to capital K times the cube of b minus a all over 24 times n squared.